Okay, why don't we get started? Welcome, everyone. Thanks so much for joining us today. My name is Valerie Belu. I work for the Center for the Governance of AI in Oxford and will be moderating this event. We'll be discussing Epoch's new paper titled, How Much Does It Cost to Train Frontier AI Models? It builds on their prior work featured in the 2024 AI Index report. With me today are three of the paper's authors, Robi Rahman and Ben Cottier from Epoch AI, and Nestor Maslej from the Stanford Institute for Human-Centered AI. We'll start with a brief presentation by Nestor, summarizing the paper's key findings with regards to the dramatically rising cost of training frontier AI models. This will be followed by a panel discussion, which will touch on the factors driving this increase, as well as the resulting implications for AI research and development, model capabilities, the deployment of AI systems across various industries and sectors, and the environmental footprint of AI. Finally, we'll close with an opportunity for the audience to ask our panelists some questions. If you'd like to submit a question, please do so via the Q&A button at the bottom of your screen. Thanks so much, and passing over to Nestor.
Yeah, very excited to be here today and very excited to be kicking off what I think should be a really excellent and exciting presentation on a topic that I think is of quite consequential importance. And really what we're going to be talking about today in the keynote, at least, is going to be some of the key findings of the paper that we've just written. And then the panel is going to be a good opportunity to unpack some of those findings, try to really make sense of what those findings are and what they may mean. And there'll be, as Valerie noted, an opportunity for some excellent kind of audience questions. Now, before we actually dive into some of the paper findings themselves, let's actually set the stage for the discussion today. There have been comments made by the CEOs of leading AI labs like Dario Amodei from Anthropic that have said that models that will be trained in the next year are going to cost around $1 billion. And I think that for those of us that are in the AI space and follow AI developments quite closely, I think it's a well-known secret that these models are becoming increasingly expensive to train. But I really think that until this year, that is, until the pioneering work that Epoch has endeavored to do, there wasn't really a lot of tangible knowledge on just how much it cost to build these models and how much more expensive these models were becoming. And these kinds of questions have a lot of massive implications for how much we can expect AI to continue progressing in the future and whether or not we think the development of AI is going to be something that is going to be widely accessible, whether universities can do it, nonprofits, or if perhaps it's something that is just going to be in the hands of industry actors. Now, Epoch maintains an excellent database of the training compute of notable models. And using this information that is already in the Epoch dataset with further information that we've collected in this project on hardware that is associated with various models, it is possible to derive some estimates on the training cost of these different kinds of systems. And a version of these estimates already appeared in the AI Index report, which launched a few months ago in April. And these estimates were one that used a cloud compute methodology, which we'll touch on a little bit more as the presentation goes along. But I think when you look at this slide, you can really clearly see the massive increase in the associated training cost of these AI models. The transformer, which was launched in 2017 and arguably set off this LLM revolution, the transformer, for those that are perhaps not as familiar, is the architecture that powers most modern foundation models. That model, we estimated, cost around $1,000 to train from a cloud compute perspective. However, if you fast forward to 2023, model training costs for certain models like GPT-4 or Gemini range anywhere from $80 to $190 million. So there's clearly been a massive spike and a massive increase in the training cost associated with these models. Now, that was the analysis that appeared in the AI index report. Let's talk a little bit about what this paper, which was just launched this week and profiled in Time, in fact, what it does and what it adds to the perspective. So I alluded to this Epoch database. There's about 1,500 models in this database. For this paper, we narrowed the analysis down to 280 quote unquote frontier models that had data on compute hardware training time and utilization. Then we collected further information on hardware rental and purchase prices for hardware that was used to train some of these models. And in addition to collecting some of this data, we conducted interviews with industry experts from labs at Anthropic and Meta, for example, to get a sense as to how they actually built some of these models to better understand cost breakdowns, and also to just do a bit of a sanity check on some of the estimates that we actually produced. Now, in the end, we were able to derive estimates or cost estimates for about 40 to 50 frontier models, depending on the estimation methodology that we used. And for those that are perhaps unfamiliar, Epoch defines a frontier model as one that is top 10 in terms of training compute at the time at which it is released. Now, again, for the sake of thoroughness, we created two estimation methodologies. The first, which I already spoke to a little bit, is the cloud rental price and training time methodology. And this methodology makes an assumption that the developers are renting cloud compute. Then there's, of course, a second methodology that takes into account the fact that a lot of model developers buy their own hardware. They purchase this hardware, and this hardware presumably also depreciates over time. So that requires a slightly different methodological approach. And we'll juxtapose those a little bit in the keynote. I mean, they yield, I think, estimations which the trends for which are relatively similar, but the details for which are slightly different. So when you estimate using cloud compute methodologies, which again you saw from the AI index, you importantly get estimates for certain models like Gemini Ultra and GPT-4, which are relatively high, but you get a growth rate in terms of costs on a yearly level at 2.6 times. And I think that kind of projection is important because it, again, accounts for where we might expect these costs to be growing in the future. Then there's the alternative approach, the amortized hardware cost approach. And again, for this approach, we are taking into account the fact that hardware can be bought by a lot of these developers and that hardware will typically depreciate over the duration of training runs. Similarly, you have to account using this approach the energy costs of training and as well the kind of cost of owning the hardware rather than actually potentially renting it from the cloud. And again, with a lot of these developers, they're buying GPUs and then using them for weeks, if not months at a time in order to do some of the training. Now, if you look at the estimates that we received or that we were able to get using this particular approach, I think most consequentially, you see a fairly similar growth rate, slightly lower at 2.4 times a year, but still fairly substantial. I think one important subtlety to highlight is that using this approach, we find substantially lower costs for GPT-4 and Gemini Ultra compared to the cloud compute cost approach. And part of the reason for this is that for some of these developers like Google, the in-house production cost for Google's TPUs isn't as inflated by profit margins, and they're cheaper to produce internally than they would be to acquire if they were bought on the open market where there can be a markup. And there's a similar point to be made about GPT-4, where typically the cloud rentals of A100s will include some kind of profit margin for the cloud provider, even at a 3-year discounted rate. So again, if you buy your own hardware, it can bring the costs down in certain cases at a fairly substantial margin. But again, from a projection perspective, where we're going in the future, the estimates for how these models are expected to continue growing are roughly similar. Now, a final thing that we looked at in this paper was the total model development costs. And of course, it's important to kind of acknowledge that the training of models is not the only thing that goes into developing these models. When you develop these models, you need to think about the compute that's spent on experiments. You need to think about R&D staff costs. So here for this analysis, we looked at 4 specific models: GPT-3, OPT, GPT-4, and Gemini. And for these models, we did an in-depth investigation as to how much these models actually cost to build and what that breakdown was proportionally. And you can see that there are different breakdowns for different developers. Certain models like Gemini 1 had a substantial portion of their cost allocated to R&D, whereas others like GPT-3 saw more cost allocated toward AI accelerator chips. Now, I think one of the important things when you look at this particular slide that is important to highlight is that people sometimes have the impression when it comes to training models that the training cost is almost entirely from the computational component. And I think this analysis really importantly illustrates that that's not completely true. You know, compute is a very significant portion of the cost, but staff costs still make up a very significant proportion, especially if you count for things like equity values. Now, we only did this for 4 models, but presumably this is an avenue for further research to not only look at the cost of training some of these systems, but also really understand how this cost is broken down on a developer model level. Now, before we actually hand it over to the excellent panel, let's talk a little bit about some policy implications. And I think there's a lot of them when we talk about the rising training costs of AI systems. So first, I think there's this kind of double-edged sword where large investment in model training may lead to capability advances, but there's also the alternative perspective. Obviously, it costs a lot of money to be building these systems. Venture capitalists are pouring more and more money into these startups. Investment in generative AI is really going through the roof, and that might conceivably lead to further advancements in model capabilities if we take into account scaling laws. At the same time, though, you know, if these models are going to reach the $1 billion mark in terms of cost, there maybe is a question to really be asked about who can actually bear this cost and how many more frontier models are we in fact going to see. A second implication concerns where this model development is actually occurring. Obviously, $200 million is a lot of money. $1 billion is a lot of money. And universities, which were once, I think, the kind of bedrock and the hotspot of a lot of AI research, are no longer in a position to necessarily building these frontier systems. So the dynamics of how research is done in the academic world have changed a lot, and there perhaps are questions to be asked about what role academics should play moving forward. Should academics be trying to keep up with industrial players, or should they perhaps try to focus their attention on other interesting questions and other interesting points? And I think the last thing to mention here is just the substantial cost of energy that is required to train these systems. This is something that also we would like, I think, as a research community for there to be more data on, as in certain developers like Meta, Alfalfa have disclosed the amount of carbon that their model training used. Other developers like Anthropic and OpenAI haven't necessarily been as forthcoming, but obviously if you're training these massive models, there's going to be a fairly high computational cost. And that computational cost is going to have a huge energy burden, and that has a lot of important implications in the long run. So that wraps up the keynote, puts you guys in a position to kind of understand what the paper is about. But again, I highly encourage you guys to read the paper front to back. Ben and Robi did an excellent job stewarding the project. And I think it's a very important paper that comes at a very important time. And I'm excited now to hand it off to the panel, where we'll talk a little bit more about some of the work that we did and some of the important implications and our perspectives on the work as well. Thank you.
Thanks so much for that excellent overview, Nestor. I would like to start by exploring the factors that are driving the rapid increase in AI training costs in a little bit more depth. Ben, what are your thoughts on this?
Yeah, thanks, Nestor, for that presentation. It was great. So the factors that are driving this, I think the key thing I'd want to point to is the continued benefits to scale that the AI industry is seeing. And this depends on the scaling laws that Nestor briefly mentioned in the presentation. So AI Labs have been researching these scaling laws, which describe how performance improves with the scale of these models, which includes both the size of the models and the amount of data that they're being trained on. And the research shows that this performance continues to improve over many, many orders of magnitude of scaling. And so that suggests that these benefits of scaling will continue for much larger scales as well. So I think that's one key thing that's driving this scaling of compute, and in turn the rapid scaling of costs.
Excellent. Would anybody else like to jump in?
I mean, I think also now there's a sense when you look at some of these models that you could actually turn them into products that are usable. And I think when you look at the real kind of seminal moment in this space, I think it was the launch of ChatGPT, and that I think there were other labs presumably as well that had a similar technology as in a similar language model that had similar capabilities. But I think what OpenAI really did is turn it into a usable product. And I think as soon as people could realize, especially venture capitalists, that there were products to be had here, I think it gave them a lot more confidence to kind of pour money into the space. And it's been really, I think, shocking to see the amount of money that's pouring in, but also how quickly the ecosystem moves. I mean, this is maybe a comment for a separate webinar, but in the AI index, we highlighted how Inflection was able to raise massive amounts of money, and then within half a year, the leadership migrates to Microsoft. So I think that the scaling has given investors a lot of confidence that if they pour money into this, they're going to get a good return. The product is going to get better. And I think these kind of labs are racing one another to ensure that no one's necessarily falling behind.
That makes sense. I see Robi nodding. Any additions to the clear commercial value in terms of factors? In which case, Nestor, so you touched on this earlier, and I thought this was very interesting. The implications of these rising costs for AI research, particularly in academia and at smaller organizations with limited budgets. It'd be great if you could expand on that a little bit more.
Yeah, I mean, I think academics need to kind of evaluate and ask themselves what their role is going to be moving forward in terms of developing actually some of these systems. There's a really good graph as well in the index, which comes from Epoch, data that they provide, that looks at where are models originating from. Are they coming out of industry? Are they coming out of academia? And basically, up until 2014, most models were coming from academic institutions, or most notable models, let's say. And since then, really a massive gap has opened up. Whereas I think as of 2023, in terms of what we looked at in the index, there were 51 notable models that came from industry compared to just, I think, 15 that came from academia. Now, it's obviously super expensive to be building these kinds of systems. And, even some of the richest universities in the world don't have that kind of money around, let alone computational resources around. So I think they need to kind of take a step back and ask themselves, what do they want to do in this kind of ecosystem? I mean, you could still make a compelling argument that it is valuable for there to be university-developed foundation models, but clearly universities can't build those things on their own. They might need some government support. And you've already started to see policy in a lot of countries like the UK, like Canada, and the US that has emphasized giving non-industry actors access to compute. But also, I think there's something to be said about maybe universities doubling down on other forms of AI research. AI is a quite broad topic. And even though scaling seems to show a lot of promise, perhaps there is another architecture out there to be developed or to be discovered that maybe requires a lot of experimentation that a lot of industry actors might not necessarily be well suited to do and to kind of engage in. I mean, I think it's funny in a lot of ways. The Transformer was launched in 2017. I don't think any of the authors of the paper at the time that it was launched could have maybe predicted the revolution that it would, set off. But you would imagine that if Google could perhaps go back in time and they knew where the Transformer was going to take people, maybe they wouldn't have been as open about that from a competitive perspective. So I think there's kind of interesting tensions in the ecosystem, and the transformer is great and has led to a lot of very high level AI systems. But I think, there's other work for academics to do. But I think the most important thing is they need to, they're not occupying the same dominant position they once were. And that requires perhaps a step back and a thought as to what they want to be doing in this space.
So we have one case here for government support, one case for rethinking the role of academia in AI research. Any thoughts from the other panelists on this? Do you agree?
Yeah, I would just like to build on what Nestor was saying with like the role that academia can still play in terms of innovation. And I'd also highlight the role that it could play in terms of like responsible AI development and safety. So with innovation, again, with scaling laws, it gives this possibility of like developing an innovation at a small scale and testing it out, seeing if it works well. And then there's this promise of that method actually scaling up really well to the larger scales that we see today. So there's really still a big role potentially for academia to play in terms of innovation by developing techniques at a smaller scale, and then this can be tried out and scaled up by industry labs, which may have more funding to actually do this scaling. And then the other thing is with safety research, often this kind of research can be done at a smaller scale to like try out ideas for like making AI behave in the way that we would like it to, and avoid producing harmful outputs. And again, those techniques have the promise of scaling up to the frontier.
So more alignment research among universities. Any final additions there, Robbie? In which case, I'd like to ask you, if AI labs are willing to spend billions of dollars on a training run, what does that imply about how capable the resulting models will be?
Yeah, great question. So Ben has mentioned these scaling laws. So these were popularized in a very influential 2020 paper by OpenAI called Scaling Laws for Neural Language Models. And these scaling laws illustrate how the loss or error rate of neural language models vary with different various inputs. Most importantly, the number of parameters, the amount of training compute, and the amount of data used. And we see that over many, many orders of magnitude, there's a very predictable relationship between how much data, how much compute, how many parameters are used to create the model, and the error or loss rate of the model. And so the loss of the model is related to how good the model is at predicting text or filling in or generating text. And so the lower the error rate gets, the better these models become at language tasks. Now, if you have tried out GPT 3.5 and GPT-4 on ChatGPT, so GPT-4 was trained at a cost of about 10 times GPT 3.5 and about 10 times more compute. And so if you and this led to lower loss for GPT-4 because it's a bigger model trained with more compute, probably more parameters as well, probably more data. If you imagine this, this difference in quality of how much better the model is at this serving this ChatGPT application and all the things you can do with it. If you take that and so if you multiply the inputs to GPT-4 by another factor of 10 and then another factor of 10, then you get to a development cost of about $1 billion. And so when you're spending $1 billion, probably you'll get something that's like, imagine the quality difference between GPT 3.5 and GPT-4. Imagine that much better than GPT-4 or double that. So there is not a perfect correlation between this loss or error rate and how good it is at these language tasks. But if the error rate gets low enough, for example, if your language model is as good at predicting what sort of code a software engineer would write to solve a certain problem, as an actual software engineer with a low error rate. At that point, your AI can be used for software development, or similarly predicting what is written in a physics textbook after, like, based on some data describing a physics experiment. Then you can have the AI do physics research. So this is just implies like very, very huge economic value of these AIs scaled up. When you spend $1 billion on the inputs, I think it's very likely that you'll get like a very valuable model that with a lot of economically useful capabilities.
I guess this implies a natural follow-up question. So how long can this trend continue, and how high could training costs get?
Yeah, I can chime in. So when trying to think about how long this could go on, one thing I would look at is just like how long has it already gone on for? And we've seen, so with scaling laws, as I said, these laws have held pretty well over many orders of magnitude of scale. And we've seen this trend in costs growing at about 2.5 times per year, going on for about 8 years. And so that sort of gives a baseline expectation that this will continue for another few years at least. And I think you'd need like specific stories or evidence for why this would not continue. Like why would the situation be different in the next few years compared to past years? One reason could just be that like the absolute amount of cost matters. Like as we get to $1 billion, $10 billion, that is reaching the entire R&D budget of Google, for example, like on the order of tens of billions of dollars. And so that suggests like there might be some limitations there. And it becomes a lot less clear like how could this increase in cost continue beyond that point, and how could scaling continue? But I don't think it's certain that it would just stop at that point, because we might see by that time we already have AI systems that are so capable that they're generating a lot of revenue and actually accelerating the revenue of these companies, which may allow them to invest even more. Another possibility is that governments may get more involved, because governments have much larger sources of funding. And so we may see more funding from government or direct involvement from government, but I think that it gets very uncertain at that point.
Would anybody else like to chime in at this point?
I mean, to me, what's interesting is I think, as Ben said, it seems like we still have a little bit to go in terms of scaling, but I think that, you know, the economics of these models then becomes a very interesting question, because I mean, $100 million is a lot of money. You know, there's major motion pictures that cost that much, if not more. You know, $1 billion is even more money, right? And you know, there are, as you kind of, I think, scale up, if presumably the costs are going to grow at a similar rate, again, that maybe puts certain companies in a position of greater advantage than others. You know, I'm thinking to myself, perhaps kind of incumbents that are already kind of well established and well situated in the space. And I think, yeah, the space has evolved in a very different way. Whereas I think that, you know, when a lot of these AI developments were really kind of kicking off, you know, GPT-2, GPT-3, I think AI was still very much a research problem. Whereas now it's not only a research problem, but I think you have to, if you're a leading AI lab, figure out a way to pay back your investors. And I think that also explains in a lot of ways the tension that has gone on at some of these companies like OpenAI with, you know, their alignment team leaving en masse. I think that there is perhaps, you know, when these companies were founded, you didn't need as much money to build these systems. Now you do, and you need to get that money from investors. It's not like you could kind of pay the model off as you kind of train it yourself. And of course, investors are going to be expecting a bit of a return. And, you know, if you need to make money, you need to ship a product of some kind. So I think that from a theoretical perspective, it doesn't seem to me that there's necessarily compelling reason to believe that, that the scaling trends might not necessarily hold true. But it would be interesting to me if we do get into the, 1 billion, if not more dollar range, how is that going to change the economics of even among industrial players who could kind of build some of these systems? Is it maybe going to even price out OpenAI and Anthropic, or are they going to have to kind of either really get their ship in order from an economic perspective, make a lot of money off their product, or ask investors for even more money?
This leads us quite naturally to the next question, which is, well, how will these rising costs of AI training impact the adoption and deployment of AI systems across various industries and sectors? How about Robbie?
Yeah, so I think there's oh, yeah. I think there's a few impacts here. First, as you've all pointed out, if the costs of developing a cutting edge model at the frontier reaches $1 billion, this puts it out of reach of like almost all developers. So this suggests that frontier model creation and foundation model creation will be very concentrated among a few actors. However, this doesn't mean that deployment or application will be concentrated necessarily. So for example, you can already go on Microsoft Azure or AWS, and they offer services where you can take a copy of their foundation model and fine tune it on your business's data or for your specific purpose. So these are already sold as services. And then these go on to get deployed in very many like different applications and products. As well, there's another thing, another cost that needs to be considered, which is the cost of inference. So training costs will be billions of dollars, but when there are very many people using your product, the costs of running the model to generate the output or to power the application, these become very substantial because you need energy and computing hardware as well. So, right. Sam Altman said earlier this year, OpenAI is generating about 100 billion words per day in to power ChatGPT for its user conversations. They're perhaps spending more on inference now than they'd spent to train the model initially. Right. So basically, the frontier model development can be concentrated among these few actors, but then many different organizations will be able to will have their own copies or fine-tuned models for different purposes.
I would also add, from an economic perspective, I don't just think productivity gains are a matter of the models becoming better. I think it's also a question of how we better integrate the models. Like, I think obviously it'd be great if, GPT-5 was even more capable than GPT-4, but there's already a lot of evidence across a variety of studies in consulting, computer science, law, that workers that use these tools, at the minimum, are quicker at their tasks, and at the maximum can do the tasks at a higher quality than those that don't have access to these tools. And I think it's important to kind of keep in mind that a lot of businesses don't necessarily have the infrastructure in place to really fully leverage a lot of these AI tools. And I don't mean like physical infrastructure, I mean more kind of institutionally how they're set up to run. And I think the kind of transition from like steam to electricity offers an interesting parallel. A lot of economists estimate that it took, over 50 or 60 years from the introduction of electricity in the mid-19th century for electricity's productivity impact to really be truly felt. And part of the reason was, if you were a factory owner in the mid-19th century and you had retrofitted the factory to work with steam, you couldn't just snap your fingers and have it be powered by electricity. Even the kind of physical component was not always the impediment. In certain cases, you needed to change business processes and business philosophies to actually really leverage the advantages of AI. So I don't think a lot of businesses have really, now figured out well how to use existing AI technology, which is already really capable. So for me, even if we stay at the current level, there's still hope that we could realize productivity impacts. But of course, if models get better and a lot stronger, there is, I think, further productivity potentials down the horizon.
Yeah, I would agree with that. I would just say that we might see faster diffusion and like adoption of AI technology compared to previous technologies like electricity, because it is very much a software-based technology, and for that reason can like integrate more easily into existing systems. But I do still expect there'll be like a significant delay in when these models are first developed versus when they actually are fully diffused and integrated and actually improving productivity across the board.
Yeah, I agree with all of that. I think even if scaling were to end tomorrow, if the labs were to stop scaling up these AI models, or if it didn't work, like if it just doesn't produce any more improvements in the quality of these models, even from GPT-4, I think there's still a lot of catch up going on. Like the effects have not been fully felt yet.
Yeah, I agree with that too. So, do we have any final thoughts before I would like to ask you? No. So, and I share this concern. A lot of people are asking about the incredible energy consumption of these models and the resulting environmental footprint. Like, how significant is the energy use of frontier AI models? And what trends are you seeing in the efficiency of these models as they scale up?
Yeah, I can answer that. So you may remember from the keynote, as part of our cost estimates, we included the cost of energy. And so we had to estimate like the power requirements for training these models and the energy consumption in order to get that cost. But we can also just look at the power and energy estimates on their own. And what we found is that models like Gemini Ultra, for example, used or required about 35 megawatts of power and consumed about 40 million kilowatt hours during training. And so we didn't look at carbon emissions in our paper, but just using like a ballpark conversion, that would be on the order of tens of thousands of tons of CO2 equivalent emissions. Now, I think that's really significant, but it's important to put that into a industrial context. If you compare that to the total emissions in the data center industry, that training run for Gemini Ultra would only be on the order of 0.01% of the total. So at this point, it's still a small fraction of total emissions from data centers. But we also see this rapid exponential trend. So power requirements, we estimate, are growing, they're roughly doubling every year, which is almost as fast as the growth in costs. And so at that rate, if that continues, we can expect gigawatt scale power capacity being needed for these AI supercomputers within a few years. And some of the largest power plants in the United States are on that gigawatt scale. So that's a truly enormous scale for AI to reach. And I think by that point, it would become a substantial fraction of total energy use.
Any other thoughts from the rest of the panel?
I mean, there's a question as well about, I think, where these data centers are what kind of energy sources they're actually using. I think as part of the index this year, we tried to, in the 2023 report, we had a feature on the carbon emission of various models. And again, this is hard to estimate because a lot of the developers don't actually release this information. So some other papers estimated it. But we extended this analysis this year, and it's not necessarily a clear linear trend because, again, some models are now training in data centers that are more efficient than those that were, run before. So even though they require, more power, so to speak, there is more efficiency. Also, if a data center perhaps is trained on or is powered by nuclear energy or wind over, let's say, coal, that also kind of impacts the kind of potential cost here. I think from a policymaking perspective, it's just important to, again, as Ben said, be cognizant of what fraction of this kind of the total data center energy is being attributed to these models. And if we can kind of create incentives to ensure that the data centers that are training these kinds of places, are using are powered by energy that is clean and renewable, because that's obviously much more positive than a center that is, powered by coal or something a bit less green.
Any last thoughts before we open the floor to audience questions?
Yeah, I would just agree with Nestor there. Like it does depend a lot on how green the energy sources are for these data centers. And I do expect, based on current trends, they are going to become a lot more green. But I think it will be interesting to see, given how rapid this scaling is at the moment, are these priorities going to compete? Like, will companies actually have to trade off between using a greener energy source and scaling up their energy source in order to power these huge training runs? So that'll be interesting to see in the future.
Yeah, any last thoughts? Otherwise, we have a question from Maxime, which dovetails very nicely with the point just made by Ben. She asks, should we expect a bottleneck in the production of, oh no, we've jumped up. Is scaling going to slow down after GPT-5 at 100 times compute versus GPT-4 because of limitations in either the power supply for data center or because of the delay of building new data centers? So if GPT-6 needs 10,000 times more compute than GPT-4 would need an order of several gigawatts of power supply, like can we continue scaling given the limitations in some resources there?
Yeah, we're looking into this at Epoch right now. So we have a new model that we're developing that simulates what are the bottlenecks to scaling up AI in the future. So we consider availability of investment funds, energy, chip manufacturing, and yeah. Pardon? Oh yeah, right. Yes, training data. So yeah, we think energy is likely to be the most likely bottleneck after 2030. I actually, during the study, I interviewed an engineer from Meta who worked on Llama, and he thinks that Meta is currently capable of, like, they have the engineering know-how and infrastructure to train a model with 100,000 GPUs, but Meta and the other labs don't know how to train with 1 million GPUs. They're like, it's qualitatively different at that scale. There are unsolved engineering challenges between what they can do now and what they can do there. As well, energy becomes a huge bottleneck. So as you scale up to that many GPUs, the power supply needed is larger than the largest power plants that currently exist. So there would have to be, these labs might get involved in, for example, requesting permits to build larger power plants. Microsoft has repeatedly entered into a deal to buy nuclear power. So yeah, this is all in service of trying to scale up models past what currently exists, like GPT 4, 5, 6. It's going to require a lot more of these things.
Okay. If there's no other comments, we've got several questions around the implications of advances in distributed or federated training, or whether decentralized training works well enough to ease bottlenecks on data centers. Any thoughts on that?
Yeah, so the labs are definitely working on this. Again, if you want to scale up these training setups past like larger than the largest power plant, maybe you need 2 different data centers each with their own power plant. Google was the first to publish a major AI model report describing these challenges and how they met them. I recommend the original version of the Google Gemini paper. It's since been edited, but there are some tidbits that were in the original that were redacted. For example, so they had to develop new checkpointing strategies. Like classic ML checkpointing wasn't working because if there's a failure anywhere in your setup with so semi-analysis speculation claims it was 2 data centers, each with 7 TPU pods, and each TPU pod at full capacity has 4096 TPU v4 chips. Actually, there are some extras, and they don't constantly run with the maximum number of TPUs. But anyway, this would be around 56,000 TPUs if this is correct. And they had some challenges, just like communicating across the 2 data centers, which are like located in different places. They even said there were so many GPUs at the scale, they would, about once a week, they would get the training of Google Gemini would be interrupted by cosmic rays hitting the GPUs and flipping bits. So they had to develop new checkpointing, saving the data, storing the calculations such that it's resilient to failures anywhere in the setup. So there's going to be a lot more of this needed if you want to scale up to multiple data centers, which might be necessary if you can't get enough power at one data center to put all the chips in one place. You might need to spread it out, which comes with new challenges.
So we've got one question from Ed. How does the panel think that non-hardware or energy costs will scale into the future? So let's consider things like staff, R&D, etc.
Yeah. So I would say the results we got for the breakdown of costs, including the R&D staff compensation, it certainly surprised me in terms of how high that fraction was. I think it's important to understand like what exactly the methodology was here and its limitations. So we looked at like the contributions listed on the papers for these models. So these particular papers actually listed, as far as we can tell, like everyone or almost everyone involved. And we sort of looked at that and estimated, okay, what sort of range do we expect? Like what fraction of time on average are people contributing to this? And in the case of Gemini Ultra, which has the highest fraction, it was about 49%, I think. It had a really large number of contributors, close to 1,000. And, you know, we think that's kind of, that can be kind of misleading in terms of how many people actually put a lot of work into it. But we tried to account for that. And even so, it was still quite a high fraction. The other thing to note is that we're including equity in this. So that does inflate the fraction by 10 to 20%, but we think equity is an actual cost that these labs incur. So that's why we included it. In terms of how it will scale, we only have 4 data points at this point, so I would hesitate to really extrapolate the data that we have into the future. I would put my money on the compute fraction growing relative to the R&D staff, just because of how quickly the compute is growing, and I just don't expect that staff can even practically scale by the same amount. So yeah, I think compute will become an even larger fraction in the future.
Any thoughts on that from the other panelists? Things other than compute that will scale in the future?
That sounds right to me. I think Ben's right.
So we've got one more environmentally motivated question. Should we expect water usage and consumption to continue scaling at a similar rate to energy consumption? And how serious is this as a bottleneck and climate risk? Does the panel have any opinions on that?
I can't really answer. I have no knowledge of what the water usage is like relative to the energy consumption, but if any other panelists have some insight, leave it to them.
Yeah, I mean, similarly, I'm not in a position to answer that question, but I think it's interesting in that I think it kind of reveals as interesting as this research was, it kind of opens the door to so many other questions, and AI is only going to grow in social significance. So, hopefully this research not only, I think, puts people in a position to understand some of these trends, but as a call to action for further research in this space and further research that explores those more nuanced questions, but also other ones about costs as well.
Yeah, I would just mention related to that we have released all our code and data that we used in this study on GitHub. So people can take that data and build on it.
We've got one more question that just came in. In terms of effective compute after accounting for algorithmic efficiency, was the step from GPT-3 to GPT-4 unusually big because of GPT-3 using a somewhat deprecated architecture, GPT-4 using MOE, and GPT-4 allowing to use extra compute at inference time? I.e., should we expect the gains in terms of effective compute to be significantly smaller between GPT-4 and GPT-5 than between 3 and 4? We also have a more general question about, you said performance improves with the scale of the models. How is this performance defined? Maybe a clarificatory explanation would be helpful there.
Yeah, so we've been trying to predict qualities or capabilities or timing of GPT-5. It's a bit tricky in that, so in the past, with GPT-2, GPT-3, GPT-3.5, and GPT-4, generally there has been about a 100x scale up between the different models. It's possible OpenAI might release something that's scaled up maybe only 10x from GPT-4 and then call it GPT-5 for marketing purposes. Yeah, so the performance of the models. So again, the scaling laws give the model performance in terms of loss, which is the error rate or difference between the text the model generates or predicts and what the text actually says in the training data. So, or well, on the test set. But this doesn't translate quite directly into, there's not a defined known relationship between the model loss and the performance on benchmarks in general. We do know there's a fairly steady improvement of benchmark performance as you scale up the model and get the loss down. And then as you improve performance on the benchmarks, these are a measure of how capable the model is. And then as the loss decreases, the model can do more valuable tasks. Was there more to the question? There was a question about the architecture of GPT-5. I don't think I know anything about that, unfortunately.
I mean, I think it's hard to predict exactly when you'll have new architectural developments that could really move the needle. I mean, presumably there is going to be more research on architectural adjustments that, could plausibly make it more efficient. But, this brings to mind to me this quote from this famous Stanford computer scientist, John MacArthur, who's, considered to be a godfather of AI. I think someone asked him, when are we going to get AGI? And he said, anywhere from 5 to 500 years. And I think his kind of point was that it's hard to know when someone's going to really think of, the next transformer or the next architecture that's really going to move the needle. I think some of these companies are betting pretty heavily that, they'll figure it out. And I think there's a lot of confidence among these labs, but of course it's hard to kind of predict these things from a timing perspective.
I just noticed one last question. Apologies if this was answered while I was reading through them. We have a question about, should we expect a bottleneck in the production of GPUs for GPT-6, which will require several million GPUs, since TSMC doesn't seem to be planning to scale production by quite that extent?
Yeah, again, I would say this is an active topic of research at Epoch AI. trying to model this bottleneck in the production of the chips that are needed to train these models. When we're trying to model this, we kind of look at a sort of aggressive scenario to see like if the industry really pushed, could it actually continue this scaling and like scale up chip production enough to meet that demand. Again, yeah, our results on this are like they're still in progress. I think it's plausible that this scaling of chip production could happen, but it is certainly like a really big change, and like chip manufacturers like TSMC would have to be on board with scaling production by these enormous amounts, and it would have to actually be practically feasible, which is something that we are still quite uncertain about. So yeah, it's an active area of research.
Do you have any thoughts from any of the panelists? Okay, so we've got one more comment here. Great paper, found it really interesting. With compute scaling at around 4.2x per year, but investment only scaling at around 2.4 per year, will investment have to accelerate even more to catch up with compute? And he mentions that obviously Moore's law accounts for some of this difference, but not all of it, in his opinion.
Yeah. So just to clarify something here, that compute scaling growth rate of 4.2x per year, that's based on a different set of models than what we looked at in this study. I believe it was all of the notable machine learning models. Maybe there's also this trend that is similar in like frontier models, but over a different time scale. So there is a bit of sensitivity depending on which models you include and what time period you look at. But in terms of the time period we looked at from 2016 to now, looking at frontier models, we get the cost scaling at 2.4x per year, and the compute scaling would be some amount above that, which more or less just depends on Moore's law or like the improvements in hardware efficiency. So the compute scaling of the models that we selected, I believe would be a bit slower than 4.2x per year, and that would account for the difference between those two trends.
Amazing. So far be it for me to want to cut it off here, but we are coming to the end of our time today. If there's no last comments for any of the panelists, I just wanted to say thank you so much to everybody for attending. And we have one last one. Can we squeeze in one last one? Okay. So we have Maxime asking, do we know about any change in scaling laws when changing the type of data used for training? So when we change from text to video data?
Our coworker Pablo has a great article, Scaling Laws Literature Review, which you can check out. Yeah, see epochai.org and look up scaling laws.
Fantastic. Thanks so much for all of the excellent questions. And thank you, of course, to our fantastic panelists for joining us today. And yeah, as Robbie just mentioned, please do follow their work, and you can visit them at epochai.org and at hi.stanford.edu. Thanks so much, everyone.
Thank you, guys.
Thank you.